And the seminar bring together people from different areas working in complex systems, and we specifically look at uh, diverse set of applications in critical transitions and complex systems. And applications have included climate science, neuron dynamics, fluid mechanical systems, all kinds of systems. So I will now invite Professor Kurtz to introduce today's speaker, Dr. Krishnan. Professor Kurtz.
Yeah, Sujit, thank you very much. I'm really very happy to introduce our speaker today. It's Professor Krishnan. He's really a world-famous scientist in climatology in different areas. He is now director of the Indian Institute of Tropical Meteorology, and his specialty is modeling of climate, but also study of climate variability. Monsoon is, of course, a very strong aspect of his research, and he spent much time also abroad in several leading institutions in Reading in UK, and Scripps in California, in Tsukuba, Japan, and he was also, I think, 2 or 3 months at PIC in Potsdam. We are very happy to have him there, and I hope he will come again. He got a lot of honors, rather recently the National Award of India for his studies. He is fellow of several academies and got also several other honors, and has many papers in first-class journals. And I'm really very happy that we also have one joint paper in 2020 in Science Advance. Maybe you will talk a bit about this. The topic looks a bit similar. And despite his activity in India, he's also internationally very active. For instance, in IPCC, he's one of the lead authors, and many other duties. We are really happy to have him here, that he took his time. His time is not so, he has not so much time. And he will give us some insight of his recent research on volcanic eruptions, ENSO and Indian monsoon coupling. Krishnan, please, you have the floor.
Yeah, thank you very much, Professor Kurtz. And first of all, thanks for this great opportunity. It is indeed a great honor for me. And also Professor Sujit from IIT Madras for giving me this opportunity. And so this work on the role of large volcanic eruptions on the ENSO and Indian monsoon coupling, this is something that emerged through a collaboration with PIC, with Professor Kurtz's group. And my student Manmeet Singh is the first author. It's actually his PhD work. And this work was actually inspired by one of the earlier group, Marawan and Kurtz, in 2005. And we were very inspired by that work. And I'll come to that in my talk later on. And so at that time, I was telling Manmeet Singh that we should start applying these type of new techniques, nonlinear techniques, to understand the phase synchronization, to understand the phase speed of complex systems. And we also had this Earth system model from our group, which contributed to the CMIP-6 and the IPCC. And around that time, we were able to put these aerosols in the model. And we had introduced the volcanic aerosols in the model. And we thought that's a nice way to, probably an opportunity to test the hypothesis which Marwan and Kurtz had proposed. So it all started, that's the story. And so thank you all once again. So I'll go to my presentation, just give a brief introduction about the ongoing climate change very quickly. So human influence has been warming the climate at a rate that is unprecedented in at least the last 2,000 years. This is from the 6th assessment report. And the warming that we have seen, now we have almost, at the time of the report, it was 1.1 degree global mean. Now we are, last year we crossed.
Can you please share your?
Yeah. Is it not seen? Can you see it moving?
No, actually, you have to click that share screen again, because you took it off, right? So.
Oh, sorry. Okay.
It's not there yet. Yeah, it's on the way.
It's there now.
It's coming. It says, yeah, now we have to get full screen.
Yeah, is it there now? Can you see it?
Yeah, we can see it. It needs to be made full screen. Yeah, it's perfect. Yeah.
Okay. Yeah. So, so once again, thank you all. So this is a just quick. I thought I'll start with a quick introduction about the ongoing climate change, which is mainly human-driven, and the warming that we are seeing now. As last year, 2023, we crossed almost 1.4 degrees compared to the global mean, compared to the pre-industrial period. And this warming, what we are seeing, can be explained only if you include human activities, especially due to the emission of greenhouse gases like carbon dioxide, methane, and nitrous oxide. And just natural variations cannot explain this warming trend. So this assessment has come out from multiple models, from multiple climate models that feed into the IPCC report through the CMIP6 experiment. And so the black line is basically the observations, and the red line, what curve is showing the simulations which have both the greenhouse gas, both the anthropogenic forcings and the natural variations, natural forcing. And the green line shows the curve which has only effect of natural forcings like solar irradiance changes and volcanic eruption. So I just marked these two periods which were associated with the Pinatubo eruption in 1992. You can see some mild cooling episodes. So the cooling can be, so these aerosols which go into the stratosphere after very large volcanic eruptions like the Pinatubo, they stay there for a couple of years or even longer, and they backscatter the incoming solar radiation. And there's also some absorption. And so the radiation at the surface is reduced. And this can reduce the global mean temperatures substantially for a couple of years. In fact, there have been big volcanic eruptions like the Tambora eruption, which basically led to a year without a summer. And many parts in the Europe and America, it had very profound impacts. And what in the future, with continued global warming, we see that the temperatures are continuing to increase. And these are some of the scenarios. The low emission scenarios, we will manage to keep the warming below 2 degrees. But in the yellow line, the SSP 245, that's the kind of the middle of the road. So we will cross it will be close to 3 degrees warming global mean temperature. The other scenarios are high emission scenarios where we'll be crossing even 4 degrees warming. So unless there are deep reductions in the carbon dioxide and other greenhouse gas emissions, so this warming is going to be very pronounced in the coming decades. And also with every increment in the warming, the changes in the regional mean temperature and precipitation, and also the soil moisture, they are going to get stronger. And you can see this is the observed warming. You can see much of the warming concentrated in the high latitudes and the polar regions. This is from the observation, present 1 degree warming, and this is what is simulated by the models. The warming is not uniform everywhere. Mostly it is in the high latitudes and the polar regions. So when we go to with 1.5 degree warming and 2.5, 2 degree global warming and 4 degree, the pattern is continuous, but the magnitudes are amplified. And associated with that, we see precipitation changes due to increased temperatures. Precipitation in the high latitudes, polar mid latitudes are going to increase in the future. Also, the monsoon is going to intensify, whereas some of the subtropical areas and also the Mediterranean and some of the areas are going to get drier. And so this dryness in some of these areas, like the subtropics and the Mediterranean and even parts of South America and southern parts of Africa and Australia, so it's going to lead to severe aridity in the future. So it's like a dry is getting drier and the wet regions are going to get wetter. as the global warming progresses. So I thought I will also show this slide because it's not only the greenhouse gases, there are other drivers like the anthropogenic aerosols, which have also masked the greenhouse gas warming. And if we, this is mostly coming from the northern hemispheric region, where the aerosols like sulfur dioxide and nitrous oxide and sulfur dioxide and other organic aerosols, they have masked the warming. And what the assessment says is, if we did not have this aerosol forcing, the global warming would have already exceeded 1.5 by that time. So the masking is about 0.4 degrees by the anthropogenic aerosols. This is very important because especially when we are talking about hydrological changes in the water cycle, aerosols have a very important role. By the way, the aerosol which I am referring to now is mostly due to the anthropogenic activities. It is not the natural ones like the volcanoes. And we also understand the temperature and the precipitation fingerprints of both the greenhouse gases and the aerosols. Again, these are from the same models. The temperature fingerprint for the greenhouse gas is a kind of uniform. It's kind of warming everywhere, with pronounced warming in the high latitudes and in the mid latitudes. Whereas the temperature fingerprint for the aerosol is mostly cooling over some of the mid latitude areas, extratropics, and the continents of the North America and the Eurasian region. And it has, you will see a interhemispheric contrast because the aerosol loading mostly dominates the northern hemisphere, anthropogenic aerosols. You have cooling in the northern hemisphere, whereas warming in the southern hemisphere. And this kind of interhemispheric energy imbalance tends to shift the precipitation fingerprint for the aerosol to the hemisphere which is warmer. So you can see the ITCZ is generally located in the southern hemisphere, and many areas tend to get reduced precipitation, including the Indian monsoon region and the West African monsoon region. Whereas with precipitation fingerprint of the greenhouse gases, you see some of the mid-latitude areas increase precipitation, also several areas in the tropics, and the subtropical areas are drier. So there are these two different drivers. The mechanisms are completely different, and these two drivers have influenced the global mean temperatures, at least in the historical past, and they have also affected the precipitation patterns. Now, what about the monsoons? This was the assessment from the IPCC, especially for the South and South Asian monsoon, where precipitation decreased from the mid-20th century since 1950s. This is a very high confidence statement, and the dominant cause being the anthropogenic aerosol forcing. This is all what happened in the past. And likewise, when we look at the East Asian monsoon region, there were areas in the northern part of China, there was a drying trend, whereas in the southern part, it was a wetting trend. And this happens to be the combined effects of both greenhouse gases and aerosols. Another important point is that in the near term, that is, when we say near term, in the terminology of the IPCC, it's a period 2021 to 2040, South and Southeast Asian monsoon and also the East Asian monsoon precipitation will be dominated by the effects of internal variability. And predicting the changes in the next 20 years, we have to take into account the effect of internal variability, which is a big source of uncertainty, and also natural forcings like the volcanoes, which are highly unpredictable. And but in the long run, when the global warming continues, so the precipitation is going to, the monsoons are precipitation are projected to increase in the future. So just a minute, I'm trying to move this bar. Okay. So these unpredictable natural forcings, they can lower our degree of confidence in the near-term changes in the water cycle and monsoons. So now we are talking about what will happen to the, when we are talking about complex dynamical systems like the Indian monsoon and the ENSO. how will these are two really very complex systems. And the question we are asking is whether large volcanic eruptions can alter the coupling of these two systems. And it has been known that big eruptions like the Pinatubo or the ones like the Krakatoa or the Tambora eruptions, they can really weaken the monsoon because of I showed you in one of my previous pictures the effect of the aerosol. Sorry. Yeah. So when you look at the temperature fingerprint of the aerosol, you see a large cooling in the northern hemisphere, or the Eurasia and the North America and the regions in the Atlantic. And this cooling can really weaken the monsoon. I'll come to that point. And so the question and people have studied these large volcanic eruptions can really weaken the monsoon. And now studies are also showing that big eruptions, they can also affect the El Nino Southern Oscillation. This is a very important, coupled phenomena in the Pacific Ocean. And these big eruptions, usually after a year or so, they tend to be followed by an El Nino. I will be coming to that. So we asked the question that whether these big eruptions can alter the coupling of the Indian monsoon and ENSO. And so this is a very complex, this is a picture of the Indian summer monsoon. It's a very complex dynamical system. We have the mighty Himalayas and also the Tibetan Plateau to the north, and we have the Indian Ocean to the south. So during the pre-monsoon and the early monsoon months, the land gets heated up. You have a thermal contrast, which sets up the pressure gradient, and there is a very strong flow of the winds from the ocean to the continent. And due to the effect of the Coriolis force, there is a deflection of the wind, which picks up the moisture from the Indian Ocean and Arabian Sea. And it also interacts with the Western Ghat mountains and also the Burmese mountains. And it leads to the formation of cloud systems, which can organize over several thousands of kilometers. And these clouds, when the water vapor condenses to form clouds, it also produces enormous amount of latent heat, and which in turn can strengthen the monsoon circulation. So this is also these winds which come from the Indian Ocean, they interact with the orography in the East African mountains. You have the highlands, and which is important for orienting the low-level flow, what we call as the Somali jet. And there is also interaction of these winds with the ocean currents. And in this region, because the water is being taken away from these coastal areas, you have cold water that comes up due to the upwelling, which brings a lot of nutrients to the surface. So it has strong, you can see this is the chlorophyll content during the summer monsoon season. So the east coast of Africa and the Arabia, you can see enhanced upwelling due to the increased primary productivity and due to the chlorophyll. But the important point is the equatorial, because there is a strong change in the Coriolis force. The equatorial dynamics is very, very complicated. And this is one of the big challenges. And also this region is, in addition, because the Coriolis parameter is very small, it's close to zero, whereas the beta term, which is the meridional gradient of the Coriolis parameter, is very large. And so the equatorial region has its own dynamics, very peculiar dynamics. And on top of that, we are putting these mountains, East African highlands, right on the equator. So this is a very, very complex dynamical system. And so it has land-sea contrast. It has also the formation of the cloud systems, the latent heat release, the interaction between wind and precipitation. And it is also affected by many phenomena like the El Nino Southern Oscillation and also the Indian Ocean dipole and a host of other phenomena. And we are now asking the question that by introducing the greenhouse gases or aerosols or putting the volcanic forcing, how it is going to impact the monsoon. So the point is, monsoon is really a complex dynamical system. And just to convey the point, this is the temperature both over land and ocean surface temperature. This is during November, December, and this is during May, June. You can see during the winter, the land is very, very cold. And by May, June, parts of the West African region and the Asian region, the temperatures exceed close to 35 degrees. And we are basically developing a strong temperature contrast between the land and the ocean. During the winter, the oceans are much warmer. And interestingly, when you see the change in the winds at the low level winds, during the winter, we have the winds coming from the high in the Asian continent. We have the northeasterly winds. And now, during the summer, there is a total reversal of the wind field. And you can see this is a picture I borrowed from Julia Slingo, with whom I worked many years back. You can see the strongest reversals happen in the Asian monsoon, especially the South Asian monsoon, total reversal of the wind field. And you also see similar reversals in the West African monsoon from the winter to the summer, and also the Austral monsoon, very strong reversals. And in my previous picture, you had seen all these regions were associated with strong thermal contrast in the pre-monsoon months. So definitely the important point is you need the land and ocean contrast to begin with, but subsequently there's a lot of interaction between the winds and the moisture and the precipitation and the clouds, which is what drives the monsoons. And so this is the precipitation pattern. You can see this is during December, January, February. This is winter. The ITCZ, we call it as the intertropical convergence zone. In our language, it is known as ITCZ. And we have we can see during winter, this is the Australian monsoon, which was associated during this time. We had the monsoon season over Australia. And during June, July, August, and even India, for that matter, even September as well, we get the monsoon rains over India. A complete shift of the ITCZ to the northern hemisphere. And this is the West African monsoon, where seasons in the Sahel and many areas, they get precipitation. And also we have the East Asian monsoon. So this is a very highly seasonal phenomena. The strongest phenomenon is the Indian monsoon in terms of the seasonal reversal. So as I mentioned, this is the rainfall distribution of monsoon rainfall distribution over India. It is not spatially uniform. The rainfall maxima is mostly concentrated along the Western Ghats and also over the Northeast India. And this is the core monsoon region over central and eastern part of India, which also receives substantial amount of rain. And we have very dry areas in the northwest and also over the Western Himalayas. And so these are the year-to-year variations in the rainfall anomaly. This is again from IMD. This time series has been constructed by IITM based on a fixed number of stations. And what we see is that there are years when you had these deficient monsoon shown by the red bars, and we had the excess monsoon shown by the blue bars. And it turns out that many of these red bars have coincided with El Nino events. That means a period of anomalous warming in the central and eastern Pacific. And whereas the excess monsoon years, above normal monsoon years, are associated with La Nina, which is the opposite phase of the El Nino, which is associated with cooling in the central and the eastern Pacific. And so the changes in the ENSO are associated with what is known as a Walker circulation, which is named after Gilbert Walker. And so normally we have the trade winds. These are easterly trade winds. That means winds from the east. We call them as easterlies. So in the Pacific, in the low level, in the low latitude areas, we have the trade winds coming. They take away the water from the Peruvian coast and from the Chile coast, and this water has to be replenished by cold water from below, and this is known as upwelling. So as the trade winds strengthen, you have more upwelling, and this leads to cooler, because when the cold water comes up, you have cooler SST, sea surface temperature, and these easterly winds, they pile the water in the West Pacific, and as the water accumulates, the oceanic mixed layer and the thermocline deepens, and you have a warm sea surface temperature in the Western Pacific, which also drives, because of the increased warming and the convergence of moisture, you have development of deep convection in the atmosphere, and these regions experience a lot of rainfall. And this is a typical Walker circulation. And during an El Nino, when the trade winds weaken, the heat that is accumulated in the Western Pacific, it slowly starts moving eastward, and the precipitation shifts to the Central Pacific, and because of that, the upwelling is reduced in the Eastern Pacific, and you have the development of the warm sea surface temperature anomaly, which we call as the El Nino. So basically, the El Nino and Southern Oscillation, that's a coupled phenomena. And as I said, the Southern Oscillation was discovered by Sir Gilbert Walker, who was in the India Meteorological Department, and he was trying to get the predictors for the monsoon. And so he tried to make correlations. He tried to find predictors for the Indian monsoon, and he hit upon this opposite, a seesaw in the pressure patterns, pressure variations between the Western and the Eastern Pacific. And this was named as the Southern Oscillation. And so when you look at the mean state of the Pacific Ocean, it's a coupled system. You have the warm sea surface temperatures in the west and the cold temperatures in the east, as I said before. So there's a strong sea surface temperature gradient. And associated with the warming, you have more precipitation in the west. And in the east, because of the colder SST, you have more of sinking motion. These are cloud-free areas, and this area is associated with upwelling. And when you say precipitation, it's basically the clouds are very deep clouds here. And due to the condensation of the water vapor and formation of clouds, the latent heat release is enormous. It drives a very large-scale east-west circulation. It is known as a Walker circulation, which rises in the Western Pacific and sinks in the Eastern Pacific. And you have the return trade winds at the surface. And so this is the general configuration. And when the easterly trade winds, they pile up water in the Western Pacific as they keep pushing the water, and the water accumulates in this region in the Western Pacific. You have a very deep mixed layer, and below that you have a region where the temperature gradient decreases very rapidly, and that is known as a thermocline. But the thermocline in the Western Pacific is very, very deep. It can be a few hundred meters, but whereas the thermocline is very, very shallow in the Eastern Pacific. And so you have a very strong temperature gradient and also a very strong gradient, east-west gradient in the thermocline. And whenever the winds, easterly trade winds, they relax, that heat content in the Western Pacific, it can start moving like a Kelvin wave. We call it as a Kelvin wave near the equator. And also the upwelling is reduced in the Eastern Pacific. So you have the development of the warm sea surface temperature anomalies, and the precipitation is shifted towards the Central Pacific. And so this is a typical situation when you have an El Nino. So basically this is the picture of the Southern Oscillation. This was what was discovered by Gilbert Walker. He looked at there are two centers. One is the Darwin in Australia, and the other one is east of the dateline, is known as the Tahiti. There is a seesaw in the pressure variations between these two places, and this he identified in the process of trying to predict the Indian monsoon. And later, it was Bjerknes who really said that the Southern Oscillation is the atmospheric part of the ENSO, the El Nino Southern Oscillation, whereas the El Nino is basically the oceanic component. And the ocean and atmosphere are strongly coupled, and which is brought, this coupled system only drives these instabilities and this is known as the El Nino Southern Oscillation. This was actually proposed by Bjerknes. And so this is again a schematic showing how the equatorial winds gather in the warm pool, they pile up the water, and you have the cold water upwelling along the Peruvian coast, and you have the warm sea surface temperature in the west. And this drives when the normal condition, or even during the La Nina, during the opposite phase, the trade winds are even stronger, and the upwelling is further increased. So you have cooler than normal sea surface temperature in the Eastern Pacific, warmer than normal temperatures in the Western Pacific. That is a La Nina, and the convection extends even further west into the Eastern Indian Ocean, and you have very strong atmospheric convection and rainfall, and very strong intensified Walker circulation. But during an El Nino phase, the trade winds actually weaken, and whatever heat is accumulated in the ocean heat content, it moves eastward. And also the upwelling, because the SST gradient, east-west gradient reduces, the upwelling also, the winds also weaken, and the upwelling in the Eastern Pacific is reduced, and you have the development of the warm sea surface temperature anomaly, and rainfall increases over the Central and the Eastern Pacific during El Nino events. That's a very quick summary. And so this is in the Pacific. Also, there are many changes that take place in the oceanic circulation during an ENSO event. What I described in my previous slide was mostly the atmospheric circulation changes. Also in the ocean, you have changes in the currents, and this was all developed as part of what is known as a Triton array, a tropical atmosphere ocean array in the Pacific, where they had these moorings which measured the ocean temperature and currents and salinity. And this was built over a 10-year period. And people could document many of these theories that were proposed to explain the ENSO. And I will not go into this YouTube. You can take a look at this. And this Triton array was later extended into the Indian Ocean and also in the Atlantic Oceans. And they have provided a very good understanding of the ocean dynamics. Just to give you an example, this was in 1997 and 98. We had 1997. We had one of the biggest, very strongest El Nino at that point of time, and you can see that this was the situation of these are the ocean temperatures, subsurface temperatures. Yeah, you can see the accumulation of heat, and these are the temperature anomalies going from January, June, November, and March. You can see that once the trade winds are weakened, the heat content slowly starts moving eastward in the form of a Kelvin wave. And by March 98, it has reached the eastern end. And later on, by July, in fact, it transitioned into a La Nina. And now, in addition to these ocean observations, we also have observations from the satellite, which provided information. These are from the altimeters. You can get the variations in the sea surface height, which tells you how much the sea level, how the sea level has been changing during these events. So during an El Nino, we have as the heat content moves eastward and the ocean starts warming, the sea surface temperature starts increasing in the Central and Eastern Pacific. The sea level also starts increasing in this region. And so this is a picture of the showing this is during November 1997, peak of the El Nino, an increase in the sea level by about 15 centimeters or so. And later on, by now, February 1999, when we had the La Nina, actually there's a decrease in the sea level. So from the satellite, we are also able to infer the sea level changes. And the contrast, when you look at the sea surface temperature change between December 1997 and December 1998, you can see this big warming. It's almost more than 6 degrees of warming in the Central and Eastern Pacific. And it's a very, very large area. And also it extends even into the higher latitudes, into the west coast of America, South and North America, whereas the Western Pacific is cool. And so this is a very major phenomena. And also from this satellite, we also get information about the ocean color. So as soon as the La Nina started picking in by July 98, and the trade winds had strengthened, the oceanic upwelling increased. You can see the increase. This is the chlorophyll has increased. So you can see that in the ocean color. And during the peak of the La Nina, due to the reduction in the upwelling, the nutrients also and the chlorophyll, they don't come up. So you can also get information about the chlorophyll changes from the satellite. Yeah. And some of the theories in the 80s, very important theories were developed for the ENSO. And one of the theory was by Kane and Zibiak. They proposed a theory for the El Nino and Southern Oscillation. So they proposed that this is the intraannual variations in the ENSO. It happens, it has a recurrence, but it occurs at irregular intervals. It's kind of quasi-periodic. It has a time scale of about 3 to 7 years, and it is maintained by deterministic interactions in the Pacific Ocean between the atmosphere and the ocean. The ocean dynamics, basically, it alters the sea surface temperature. And once you change the sea surface temperature, you are going to change the winds, the atmospheric winds, and the convergence of the moisture and the heating. And if you are going to change the heating, the resultant changes will in turn alter the wind and the ocean dynamics. So it's a coupled phenomenon. And they could explain some of the formation of the sea surface temperatures during El Nino years in the central and eastern Pacific. And also they talked about the movement of the heat content and the currents in the ocean with a simple model. And later on, this was another paper, detailed paper, a model for the ENSO by Zibiak and Kane, where they suggested this. There's this basically a coupled interaction of the atmosphere and the ocean. There is a tendency of phase locking of the anomalies, which depends which is dependent on a number of parameters, and essentially that affect the strength of coupling between the atmosphere and ocean. So once you have a stronger coupling, that means the oscillations are larger, and also the time scale becomes larger. And this was a very simple model of it was a shallow water model of the atmosphere, which is driven by the temperature, sea surface temperature. But they prescribed the annual cycle of convergence. This was prescribed from the observations, and and monthly convergence. And the temperatures were also it had a perturbation temperature and a mean temperature from the observation. And the ocean had a two-level model where the temperature variations, especially in the Eastern Pacific, it depends on the vertical variation of the temperature. Basically, to incorporate the changes in the entrainment due to the upwelling changes, they had a two-layer model. And this model could produce many of the irregular oscillations of the ENSO. This was in the 80s. It became a very famous model. And later on, many other theories also came to explain the ENSO phenomena, which has a typical time scale of about 3 to 7 years, irregular but quasi-periodic. And there were two important theories I will tell. One is what is known as the delayed oscillator theory, which was proposed by Suarez and Schwab, and the other one by Battisti and Hurst, more or less around the same time. Basically, in the equator, you have there are two important waves in the equatorial region, because equator acts as a wave guide. And so two types of waves. One is known as the Kelvin wave, which usually is confined along the equator and also along the coast. And these Kelvin waves, they propagate eastward, and their phase speed is much faster compared to the Rossby waves. The Rossby waves are also long waves, but they propagate westward. Their phase speed is much slower. And these were identified by Matsuno long back in 1966 in his pioneering paper. And basically, this delayed oscillator theory by Suarez and Schwab, what they were applying stress right on the equator, a westerly wind stress that is from the west, the ocean is going to respond, because to the east, it is going to deepen the thermocline. This is in the form of a Kelvin wave. And to the west of it, you have a pair of these Rossby waves. These are off equatorial. The Kelvin wave is mostly confined to the equator. It doesn't have a meridional component. The Rossby wave is off equatorial, and you have a pair of these Rossby waves. And so you are applying a wind stress, and this is going to change the thermocline depth. Means it is going to change the sea surface temperature eventually. And yeah, so this is the picture. This is just showing the time sequence of this is from again based on the delayed oscillator. So this Kelvin waves, this is the initial perturbation when you apply this wind stress forcing at time 0. And 25 days later, you can see this Kelvin wave has propagated eastward, and the Rossby wave is moving slowly westward. And this is at the time of 50 days, 75 days, and so on. And this is going on up to 275 days. So due to the faster speed of the Kelvin waves, it reaches the east coast. And then once it reaches there, it gets reflected from the east coast, and it moves westward. Likewise, the Rossby waves that are going towards west, they also reflect from the western coast of the West Pacific, and again it starts moving eastward. And so the delayed oscillator theory, they basically accounted for this delay due to these waves, transient waves, how it can affect the sea surface temperature. So they kind of introduce a negative feedback, which can really, because once you, in the Central Pacific, when you have a El Nino phenomenon, the coupling is strongest in the Central Pacific, where there is an accumulation of the warm water, and then the convection develops. So that is the region where you have the strongest coupling between the atmosphere and ocean. In the Western Pacific, you have a very deep thermocline, and the sea surface temperature is warm. So it can affect the atmospheric convection. The high sea surface temperatures can affect the convection. In the Eastern Pacific, it is the winds that affect, because of the upwelling, because the winds can drive upwelling, it can bring the cold water from below. The sea surface temperature is affected by the winds. And so basically in the Central Pacific is the region where this instability, the coupled instability, grows very fast. And what Suarez and Schwab did was to introduce a delay. In this delayed oscillator, they included the effect of the transient waves, which is a negative feedback. And they could explain many of the oscillations, oscillatory behavior of the ENSO phenomena, including the irregular nature of the oscillations, intra-annual variability. And there were other theories in addition to the delayed oscillator theory. There was another theory known as the recharge-discharge theory by Jin. This works more like a capacitor theory, where in the West Pacific, if you are charging the West Pacific, the heat gets accumulated, and once the wind slackens, then it starts discharging. This was another important theory. And there have been several other theories known as the Western Pacific oscillator, the advective reflective oscillator, unified oscillator, and so on. So there has been a great deal of understanding the ENSO phenomena. Still, there are open questions. For example, what really triggers a El Nino? And many of these models, once a El Nino is triggered, they can capture the progression of the El Nino. But what is the initial trigger is not well understood. And in fact, now some studies suggest that when you have this burst of westerly along the equator, this typically happens during a phenomenon known as a Madden-Julian oscillation, which is a kind of a patch of convection that moves along the equator, and it has a time scale of about 30 to 60 days. And so when there's an active phase of convection, to the west of it, you have this patch of westerlies. And these westerlies bursts can trigger these downwelling Kelvin waves, and that can be a trigger for the onset of a El Nino. But many of these questions are still open. And once these waves are triggered, there is a kind of a Bjerknes feedback mechanism, ocean atmosphere coupled feedback mechanism, which allows this sea surface temperature to grow. And why? And ENSO is of great importance because it affects global impacts. And during El Nino years, many parts, of course, in the oceanic areas and some parts of America, it becomes wet. But for example, the Indian monsoon, we have a dryness, and also regions in the maritime continent, Indonesia, Australia, they can be very dry. Also parts you can have dryness over Africa, except the eastern part of Africa. And some places in North America, Central America, they can get wet. And South America, you can experience dryness. These are the global impacts. And it has, of course, there is a seasonal dependence also. Seasonally, the ENSO impacts are usually strong during the northern winter, and they can also affect the circulation patterns in the extratropics. And but generally, when the El Nino happens, it weakens the monsoon. There's a reduction in the monsoon precipitation. The Walker circulation becomes weak, and you have reduced precipitation over India and over the maritime continent and even Australia. Okay, and people have studied this in observations right from Walker from 1924, from the and this famous paper Walker and Bliss and so on. And many studies also came from IITM and several others. And also there were model experiments to understand the effect of sea surface temperature on the monsoon and the global circulation. Two such studies. One was by Professor Keshav Murthy in 1982. This was the first simulation with the GFDL model when he worked with Professor Suki Manabe. And so they showed that the Central Pacific, when you put the warm sea surface temperature anomaly, it has a big influence on the general circulation on the monsoons. And the other paper by Krishna Kumar et al. Was also my colleague at IITM. And I'll come to one of his papers which showed how the ENSO monsoon link has been weakening. And subsequently, they did some model experiments. So I thought I should highlight. So the ENSO monsoon connection has been addressed both in observations and models. Several studies have looked into this. And in fact, when you take the sea surface temperature anomaly, this is a very interesting paper by Vimal Mishra, works in IIT Gandhinagar. He looked at the relationship between sea surface temperatures and rainfall over India and global sea surface temperatures. And so they did a maximum covariance analysis to identify these coupled patterns of SST and Indian summer monsoon rainfall variability. This is June, July, August, September. The first mode turns out that it's a kind of when you have a deficit rainfall all over India, and this is associated with a kind of a warming pattern in the Pacific, warm sea surface temperatures in the east, central and east, and cooling in the west. And the second mode of variability is the one that has reduced rainfall over the Indo-Gangetic plain and warming in the Indian Ocean. And this looks more like a break-like situation. There's a break in the Indian monsoon when you have less rainfall over this core monsoon zone in the Indo-Gangetic plain. This is associated with the Indian Ocean warming type of pattern. So, and then in 1999, there was a very important paper by Krishna Kumar et al. They noted that the ENSO and monsoon, which people have studied for decades, that relationship, there's an out of phase relationship. So whenever you have an El Nino, you have less monsoon and vice versa. They found that this relationship has been weakening. They said that when you look at a long time series and this relationship is not stationary, it is non-stationary. And in the recent years, this correlation has weakened. And they said that this weakening could be because of the increased surface temperature over Eurasia in the winter and spring. And this may increase the land-ocean thermal gradient, which is conducive for a strong monsoon. So even if you have an El Nino, the effect, it can weaken. And they also argued that there could be a possible southeastward shift in the Walker circulation associated with ENSO events, which might have led to reduced subsidence. And this paper led to a lot of new ideas. And Very importantly, there was a paper by Marawan and Kurtz in 2005, and they came out with some very, very important findings, which was the motivation for our study with Manmeet. And what they found was, they said that simple correlation is based on, we are only looking at the amplitude variation of two signals, and you are not really considering the phase information. And so when we are considering oscillatory systems like the ENSO or the Indian monsoon, they also say Indian monsoon can also be put as an oscillatory, classified as an oscillatory system. There are two things. You have to also look at the phase and also the amplitude to describe the oscillatory behavior. What they found was there are epochs of phase coherence between ENSO and Indian monsoon. And so this is a nonlinear technique. Usually using the linear techniques, you cannot uncover this phase information. You need to follow a nonlinear approach. And what they found was we present a modern method in nonlinear time series analysis to investigate the relation of two oscillating systems with respect to their phases, independently of their amplitudes. We study the difference of the phase dynamics between ENSO and the monsoon on interannual timescales. And their findings, they identified districts, especially two intervals of phase coherence, 1886 to 1908 and 1964 to 1980, corroborating earlier findings from a new point of view. So basically, they're arguing that during these two periods, there was a phase coherence between the ENSO oscillation and the Indian monsoon oscillation. And they further showed that this, through a statistical significance, this coherence is very unlikely to be a result of stochastic fluctuation. It cannot be random. So there was another paper by Gershunov. So in fact, they had argued that if you take two random time series and do a low pass filter, you can get this changes in the correlation. But this study, they argued that this cannot be an outcome of stochastic fluctuations. And they also detected so far unknown periods of coupling which are invisible to linear methods. And the findings suggest that the decreasing correlation during the last decades might be a typical epoch of the ENSO monsoon system having repeatedly. And one last point they made was, I'll come to this. This is what most important. The high time resolution of the method enables us to present an interpretation of how volcanic radiative forcing can cause the coupling. And that was the real motivation for us to take up this study later on. And this is again a material that I've borrowed from Kurtz's book, Pikoski, Rosenblum, and Kurtz, where they talk about how to do the phase reconstruction. So when you have two systems which are exhibiting self-sustained oscillations of slightly different frequencies, and if you bring them into contact, you can see that when the coupling strength is low, this actually the systems, they tend to evolve independently. But if you increase the coupling strength, at the first the frequencies start adjusting, and later on the phases describing the oscillations get locked. So you have two pendulum. In fact, this problem was first noted by Huygens, Christian Huygens, a Dutch mathematician, astronomer, and physicist, was working with pendulum clocks. And so if you have two pendula which are oscillating at slightly different frequencies, but now you couple them through a beam which is not very rigid, through a fixed beam but not very rigid, the oscillations of one pendulum can feel the oscillations of the other, and they can feel the presence of each other, and the motions can get synchronized. So this was a very, very important finding, and there has been a lot of work on this phase synchronization. So in fact, I am also learning some of these things from these papers. And how do you do this? So there is something known as the phase coherence analysis, which is applied PCA analysis. So to understand the phase relationships between two systems, basically we have, in this case, we have the time series of the ENSO and the Indian monsoon. Of course, we have to apply a kind of a low pass filter to cut off some of the, to remove some of the intra-annual oscillations. And to do the phase, to understand the phase variations, you have to use what is known as the Hilbert transform. So you have a time series or a signal ut. When you apply a Hilbert transform, basically you are convolving the signal. You do a convolution with 1 by pi t series, and and when you do this convolution, this PV is the principal value or the Cauchy principal value, which is basically, this is a complex number, and when you want to get a value for this PV, basically you have to when you're dealing with improper integrals, and you have to get rid of these singularities. So you have to get the non-singular value to get the principal value or the Cauchy principal value. And once you do this, from this you can actually, from the Hilbert transform, you can do the Hilbert transform, and then you can, from that you can extract the phase. The phase is a complex number which has a real part and an imaginary part. The phase turns out to be just the tan inverse of y upon x. And there was another important paper which they describe in this paper, Marwan and Kut. This is by study by Osipov et al. They said that instead of, they used by geometrical reasoning about the curvature of the phase space trajectories. So instead of taking the ratio of y, the imaginary part, by the real part, why not take the derivative? They said you can take the derivative of the y dot by x dot and take the tan inverse. And in fact, that turns out to be a very effective method of retrieving the phase from this time series. And I'll come to that. And so the method Marwan and Kurtz followed was, you have this time series of the NINO3 index where there is a low pass filtered, and you have the all India rainfall. This is again from the monthly data, a low pass filter data. You do a Hilbert transform. This is we show here in this the NINO3, the Hilbert transform of the NINO3. This is the solid line is the NINO3 time series. The dashed line is the Hilbert transform. And now this dotted line which you see here is the amplitude. That is the square root of x square plus y square as a function of time. And it has plus or minus. So you have one on the positive side and one on the negative side. And just to identify the important peaks, they have taken a cutoff of a greater than 0.8. And so one of the things that you have to do is, you have to do a phase space analysis of this Hilbert transform. This is for the NINO3. Once you plot the NINO3 index and its Hilbert transform, you have to see whether it is going around a common attractor. That's a very, very important thing to have a self-sustained oscillatory system. And this is for the derivative of NINO3, that is the NINO3 d NINO3 by dt and its Hilbert transform. You can see that compared to the NINO3 itself, the time derivative of that is going around the single attractor. So it's a kind of self-sustained oscillatory system. Similarly, you can do this analysis for the Indian rainfall. You will get the oscillations going around the single attractor. So meaning that these are self-sustained oscillating systems. And you can unwrap this. So there are techniques with the Hilbert transform, you can unwrap, and then you can get this time series of the Hilbert transform. You can see how the phases of phase propagation is happening. The solid line is the phase of the NINO3, and the dashed is the monsoon, the phase of the monsoon oscillation. You can see the monsoon oscillation is moving much faster, is moving at a faster as compared to the phase of the ENSO, the NINO3 index. And so once you have the phases of these two systems, you can actually do the phase difference and see whether there is a phase coherence. And so this is the time series of NINO3. And so with the unwrapped time series, when you say unwrap, after every one oscillation, you add 2 pi to it. And so you keep on adding 2 pi for after every oscillation, and you can get this. And you take the difference in the phase between the NINO and the Indian monsoon, and you plot this series, the phase difference series. And what they found was there are these periods where the phase difference is almost constant. It doesn't change. These plateaus, what they call. And these are the periods of phase coherence, where the ENSO and the monsoon, you have period, this is one period, and you have the other one here. And these two periods, you can see very strong epochs of phase coherence. And this period, there are some periods like the one that you see here, where the monsoon oscillations are, the phase speed is is almost 2 times faster compared to the ENSO oscillation. Likewise, you see one more epoch here where the monsoon oscillations were much faster. And there's a third variety where you don't see very well-behaved oscillations like the one here. These are irregular oscillations. So what is really important for us is to the phase, why these are epochs where you have a very good phase coherence between the ENSO and monsoon systems. Yeah.
Krishnan, excuse me, about 5 minutes, please.
Yeah, okay. I'll try to wind up very fast, and it'll take maybe 10 minutes. And now we have this, there was a paper by Kodri et al. They looked at the Nino 3 SST. Basically, they said that if you have big volcanic eruptions like Pinatubo or Agang, typically after a year after the eruption, you can see a warming increase in the Nino Central Pacific. And basically, they have removed the tropical mean SST. So it can lead to a El Nino-like pattern they proposed. And basically, their argument was this was based on model simulations. So when you have a kind of big volcanic eruption, yeah, actually the motivation, sorry to go back. Yeah, so these periods of coherence, what Marwan and Kurz, you can see a big volcanic eruption. There is a radiative forcing here. And this one also was preceded by a volcanic eruption. And you can get these periods of phase coherence. And also this work by Kodri et al., they argued that if you have these big eruptions like the Pinatubo, it can basically lead to more cooling. Why I am showing especially over the African region and the Atlantic, I showed in my earlier picture also. So once you are reducing the temperatures there, and it will reduce the sea surface temperature, and also it will drive the winds in this region, and also it will reduce the precipitation. Also, you see a reduction in the precipitation over the Indian region and the West Pacific. So you will have anomalous westerlies, which will push the water eastward, deepen the thermocline. You have development of warm sea surface temperature anomalies. And by year one year later, you can have a kind of El Nino kind of pattern developing and a weakening of the Walker circulation. And so based on these works, we said that whether you can have a coupling of the ENSO and the Indian monsoon in response to a very large volcanic eruption. And what we did was we used paleoclimatic reconstructions and last millennium simulations, and also targeted climate sensitivity experiments, and also various analysis techniques. Our main result is that when you have these big eruptions like the Pinatubo or Krakatoa, it enhances basically it increases the angular frequency of ENSO. And so there's an increase in the phase speed of the ENSO oscillations. And this leads to a phase synchronization of the ENSO and Indian monsoon oscillations. And so this has important implications for improving the seasonal forecast. So how we did was we took the last millennium simulations from the PMIP3 models. We used the IPSL model, which had run this from 850 AD to 1850. And these are the Nino 3 variations from the Central Pacific. And we also have the Indian monsoon rainfall time series. We did this we did all this analysis of the phase space analysis, what was done by Kurz, and also the phase coherence analysis. What we noticed was there are periods. This is, of course, the 1,000-year period. And during this last millennium, there were many volcanic eruptions that happened. And you can see that there are many periods when there is a phase coherence between the ENSO and Monsoon from the model. And we also plotted the volcanic radiative forcing, some of the big volcanic eruptions. You can see them here. And we also did a statistical analysis based on a twin surrogate method. And the phase, what we find is the probability density of the phase difference between the ENSO and Monsoon that is produced from this is actually statistically significant, and it cannot be explained just by the null distribution. And the most important thing is we looked at the angular frequency of ENSO. Basically, when we looked at the angular frequency, that is the rate of change of the angular velocity. So we took the phi, we took the rate of change of phi, and we had two categories. One which was preceded by a volcano in the last 4 years, and we had the other category of angular frequencies which did not have a volcano. And so we did a quantile mapping, and you can see this is to see whether the two distributions are different. And when we do a QQ plot, we see that there is a higher angular frequency following volcanic eruptions. So the cases where we had it was preceded by a volcanic eruption, the angular frequency increased. That means the ENSO phase speed increased, and this is statistically significant. Although there is a slight decrease in the angular frequency of the Indian monsoon, it was not statistically significant due to the volcanic eruption. And we also did other tests like the event synchronization, whether these eruptions the change in the frequency and the change in the it occurred during the volcanic eruption. So we had the event time series of the ENSO and Monsoon, and we had the event series of large volcanic eruptions, and that relation is also statistically significant. And lastly, we had our IITM Earth System model, as I said, where we had introduced these volcanic eruptions in our model as part of the CVIP6. And what we did was we did several targeted experiments. Basically, we took the case of Krakatoa, which happened in 1883. Why we took this Krakatoa was this was one of the major eruptions. However, it was not followed by a El Nino a year later. And this was a very strong cold phase of the decadal ENSO. And also the eruption happened sometime in August, and which was quite late in the monsoon season. What we did was we had a 100-member realization of the. Actually, what we did, we had a pre-industrial control experiment where we ran the model for 600 years. So we identified 100 initial states from this model. We started as the reference. And what we did was with 100 initial conditions, we had out of these 100 initial conditions, 47 were corresponded to neutral ENSO conditions, and 29 were cold ICs, that's like a La Nina, and 24 was a El Nino type initial conditions. And we made this 100-member run starting from 1st January 1883 up to 31st December 1885. And we saw how each member is moving. And by the end of December, January, February 84, 85, out of 29, 7 of them transitioned to cold. And out of 29, 9 went to neutral, and 10 of them transitioned to warm. Likewise, we did same analysis for the neutral initial conditions and also from the warm initial conditions. And also we selected some members only corresponding to the 26 members corresponding to the cold ICs. And we also increased the strength of the volcanic force to 4 times Krakatoa. And then we saw what happened. And we had another case where we decreased the forcing to 1/4 of the volcanic forcing of Krakatoa, and we had a 40-member realization. What we found was, starting with different initial conditions, this is the aerosol optical depth that we see during the Krakatoa. starting from 1883 to end of 1885. By the end of year one, you can see a El Nino like these are, we look at the member to member difference between the reference run, that is the pre-industrial reference run, and the one where we applied this forcing. You can see by the end of year one, whether you start from a neutral or from a warm initial condition, it makes a transition to El Nino-like situation. Starting from the cold case, we transition quickly into a warm phase, and then again it comes back to a neutral, and then a cold phase. And when we look at this composite at the during the end of 84 to 85, you can see a major cooling in most parts of the north extratropics over the Eurasian region, whereas a El Nino-like pattern in the eastern and central Pacific. And because of this interhemispheric gradient in the temperatures and the energy, these are the shortwave radiative forcing at the surface. The precipitation shifts to the southern hemisphere, and there is reduced precipitation over India, Africa, and also the Western Pacific. And also there are changes in the ocean thermocline, which deepens in the central and eastern Pacific and eastern Indian Ocean. So ENSO-like pattern is reduced and the monsoon weakens. And this feature comes out even more prominently when you increase the magnitude of forcing, the strength of the volcanic forcing. You start getting a El Nino-like pattern. And similarly, you can look at these spatial patterns, these are temporary anomalies. Typically, we say that big eruptions, the ENSO oscillations, the angular frequency increases. That means the phase speed increases, and you tend to get the ENSO-like pattern, and monsoon precipitation decreases. We also did different from the paleo proxy data. We had different proxies of ENSO and Indian monsoon, 14 different proxies of ENSO and 11 proxies of based on corals and speleotherms and also tree rings. We did a Bayesian analysis to see what happens to the ENSO and monsoon co-occurrence if there was a volcano and if there was not a volcano, all kinds of combinations. And in general, we found that the probability of a ENSO and monsoon coupling prior to a volcano is much stronger. The probability increases as compared to the coupling between ENSO and monsoon without a volcano. And lastly, we also looked at the tree ring data, which has provided information about surface temperature, Cook et al. Data, which showed that during these volcanic eruptions, there was major cooling over the Asian landmass, Eurasian landmass. So now the question is, there was a big, these are my last few slides. We had in 2022 a big eruption known as the Hunga Tunga eruption in the southern hemisphere. It was a very powerful eruption. This is a Himawari satellite, and we threw up a lot of these aerosols that went into the stratosphere. Also, water vapor went into the stratosphere. And now the question is, when you look at the sea surface temperature, the temperature changes. You can see that during 2020, 21, and 22, there was a La Nina known as the triple dip La Nina. And by beginning of the eruption happened in December 2021 and January 2022, it still continued. And by early 2023, we were transiting to a neutral ENSO, and later on an El Nino picked up in the later part of 2023. And now still the El Nino continues. And this is just to show the picture. Now, these are so during February and March 23, still the cold temperatures were there. Later on, the warm temperature anomalies developed, and the Nino 3.4 temperature was almost 1.9 degrees. And this is the sea surface temperature change during the last recent period. And the forecast, now when you look at the forecast from January 2024, by May or June, is going to go to a neutral, ENSO neutral. And in the later part, by July, September, it is going to transition to a La Nina. This is what the model forecasts are increasing. Now, and also the monsoon, when we look at the 2023 monsoon, it was initially till August, it was pretty deficient. Situation was pretty bad. Later on, in the later part of September, it made up. Still, it was a kind of a negative anomaly. All India was about -6%, and so El Nino did have a profound influence on that time during the last monsoon, 2023 monsoon. Now the question arises: what is the role of the 2023 El Nino and the Hunga Tunga eruption on the 2023 El Nino and the Indian monsoon? So when we look at the aerosol extinction from the SAGE satellite, you can see these aerosols very high in the stratosphere. And the question is, how did it affect the 2023 ENSO monsoon system? Yeah, so this is my last slide. So basically, the Indian monsoon, what we think is the large volcanic eruptions, they provide an important forcing and for predicting the Indian monsoon, and it's an important driver. And so it helps us to predict the monsoon better. And this is what it comes out from this work. And the phase synchronization between ENSO and monsoon is a very important aspect that we have to consider. And also there are regional geoengineering applications because now people are thinking that to reduce global warming, some people say that you can introduce these aerosols in the stratosphere. They call it as the solar radiation management to block the sun rays from reaching the earth. Of course, it has other impacts, like, by blocking the incoming radiation, as we saw, it can affect the monsoons, it can affect the precipitation, it has other impacts. So we really need to understand these mechanisms and scientific questions. So with this, I want to end my talk. Jai Hind. Thank you.
Okay, yeah, thank you very much.
Thank you.
Krishnan.
I'm sorry.
Very great story. Now we open the QA part. Who has questions? Maybe the Indian colleagues can manage the QA thing. You know better how to.
Jürgen, can I stop sharing?
Yeah, please.
Can you see the chat box? Or should I read out the questions?
Yeah, just a minute. If you can read out, that will be nice.
Okay, so the first question is from Govindaswamy Bala. The eruption in high latitudes would have different effect on Indian monsoon compared to tropical eruptions. Can you discuss the dependence of the Indian monsoon response on the latitude of eruptions?
Yeah, I think that's a good point. So the latitude of eruptions makes a difference. I think there have been quite a few papers, but we also compared some of our results, for example, with the reduced volcanic forcing. Some of the results, it had similarities with an extratropical eruption because Pausata and some people, they have put the eruption in different places. And yeah, it's not going to be uniform. It depends. The latitude is important, but by and large, by the time you make after the eruption, after about few months, the aerosols are distributed all over the stratosphere. So I think that's what we think. But yes, I understand that there could be differences.
Okay, I request the audience to type their questions in the chat box so that we can take them up as they come in. I think sometimes they take a few minutes for the questions to come. So in the meantime, I have a question. So I see this very interesting model where you have these oscillators synchronizing. Do you think it is worth trying to extend it to treating each of these as a distributed set of oscillators and look at it?
Yeah, that actually, if you see this 2023, it was not only ENSO, also in the Indian Ocean, there was a Indian Ocean dipole that appeared. So whether that is an oscillator, now we can have 3 oscillations, ENSO, monsoon, and IOD. And now what is the effect of these volcanic eruptions? So the Hunga Tunga probably is a very important, it's a good example to address this problem.
Thank you. Yeah. Are there more questions?
Yeah, maybe what can one speculate about forecasting? You mentioned already we have 3 such oscillators, but how could this volcanic activity change the forecasting? Would it be
Yeah,
improving or?
yeah. So what I think is right now when all these coupled model forecasts, they are initialized with the atmospheric initial conditions and they are initialized with the ocean initial conditions. And then you make the predictions for the next 6 months or 9 months and see how this coupled system is evolving. Now, when you introduce a volcanic forcing, you are also introducing your radiative changes. It's not only the initial condition. So as the model is integrated, you are introducing a forcing in the system, which is going to alter the radiation from the incoming solar radiation. And that can have an implication for the for better prediction of the monsoon.
Okay, yeah, thank you.
I do not see any.
Sorry, I exceeded my time. But
Yeah, that's okay. I do not see any more questions. So, does anybody have any questions? You can type on the chat box. Yeah, I think there is another question. How is the East Asian monsoon getting wetter related to the aerosol distribution?
yeah, no, I think East Asian monsoon that was more of I was mentioning in my that was about the anthropogenic aerosols, not the volcanoes. That was a combined effect of both greenhouse gases and aerosols. So in the north, the drying was more in the north, where the aerosol loading was there. The southern part is a more of a GHG impact. So it's a combination of both GHG and the aerosols, which leads to that pattern, north-south pattern.
Thank you.
May I ask another question? We
Yeah.
have also volcanic-like activity in other parts, especially in I think Iceland and Greenland. Could we also expect such changes of interacting oscillators, say Arctic oscillation, which other things due to that activity?
Yeah, I think yeah, that's a very interesting question. And yeah, this Pausata's group, they have done a lot of work on this, putting these eruptions in different places. And yeah, so Iceland also, I think 2023, there was a big eruption in Iceland. Yeah, that's a very important problem.
Okay.
Yeah, yeah.
There's a lot of things to do in future.
That's right. That is right. That's right. It has, yeah. And only thing is doing these realizations from the model. It takes a lot of time and resource. Even for one Krakatova, it took us not many experiments. So
Yeah, yeah.
What do you think would be the long-term effect of anthropogenic activities with respect to the interaction between ENSO and Indian summer monsoon?
okay. So what there are two actually in the fifth assessment report. What it argued was with future warming, as greenhouse gas warming continues, you will go more into a El Nino type of situation. This was the assessment. But that view has been now challenged. Now people are telling that when we look at this is especially from the Columbia group, what they have shown is, in fact, the Walker circulation has strengthened. And although the global warming has happened, Walker circulation has actually strengthened, and you are not getting a El Nino-like pattern. You are getting more like a La Nina type of pattern. And so there are deficiencies in the climate models, especially in the cold tongue. And so how global warming is going to affect ENSO, I think that's still an open question. But many people think that would also lead to a strengthening of the Walker cell.
Okay, so I think a lot of excitement ahead with all this open questions.
Exactly. Yeah. And monsoons are also projected to intensify in the future as global warming continues.
I think we are out of questions from the audience. So both Professor Kurtz and I would like to thank you.
Thank you, Professor Sujit.
To accept our invitation, and there were a lot of audience from all over the world listening. Great service to the community, and it's also bringing the nonlinear dynamics community and all the things we know from that and bringing it to full-fledged application in climate sciences. Professor Kurtz, you want to say the final words?
Oh, I thank Krishnan very much for this great talk, and also our Indian friends, our Chennai friends, for organizing all these things, which is not easy. And it was really another important chapter in our series, and I hope for very exciting new ones. Thank you very much.
Thank you, Professor Kurtz. Thank you, Dr. Professor Sujit, and thank you, everyone.